Well, good afternoon, everyone, and welcome to SeptembRSE presentation session 6. I can't believe we're up to number 6 already. Just as a reminder, this session is being recorded. We have 3 super sessions for you this afternoon. Each of them, as usual, will be 20 minutes long. We'll have a 5-minute break, for, 5-minute session of questions, which we'll do via the Slido. So please get the Slido up with the links in the chat and pop your questions into there as we go. And then between the second and third talks, there will be a 5-minute comfort break. So we have talks this afternoon from Luke Abraham from Cambridge, Ben Thorpe from Swansea, and Oscar Giles from the Turing Institute. And we'll kick off with Luke. So over to you, Luke.
Thank you. So hopefully everybody can see my screen. And so yes, thanks very much. I'm going to talk about some training that we run in Cambridge on the model that we run and how we turn this from being an in-person event to an online training event this year. So I'll talk a bit about what the model is we're actually training people how to use, what that training involves, how we used a virtual machine to do this and running this on the Jasmine and Managed Cloud, and then how we actually ran the training this year. So what is the UKCA model? So the United Kingdom Chemistry and Aerosols model is an atmospheric composition model. So this is where we simulate the chemistry and aerosols in the atmosphere, and it's built as part of the Met Office Unified model. And it's important to think of this rather than, this is the exact chemistry or the exact aerosol configuration you're going to run. It's designed to be a framework for putting chemistry and aerosol into the unified model. So we have, 4 or 5 different chemistry schemes, a few different aerosol configurations that can be run in it. And the idea is that people are able to then change it and use it how they like. And so the training is designed to get people used to how to change this model. The unified model itself is quite a big and old model. It's nearly 30 years old. It's got about 900,000 lines of code, mainly in Fortran. And the important thing about the UM from the perspective of me kind of doing this work is that it has a lot of complex dependencies, which are written in Python 2 primarily. So rather than kind of editing the name list in a text file, there's a whole graphical name list editor called Rows, which is part of the kind of whole build and run system they have there. There's this Silk workflow engine that's used, which kind of schedules the jobs, runs the various tasks, and everything's managed using something called FCM, which is a Perl wrapper mainly around subversion, but it also does other things like the build process and various other things. So all of this is actually quite complex. It means that if you're an ordinary person at a university wanting to use the UM, it's very difficult for you to install this yourself. You kind of have to have it installed centrally. And so part of what National Centre for Atmospheric Science does is provide support for the UM on the National HPC, install it and provide training courses in how to use it. And in terms of the training that we do in UKCA, we start with a very simple question, which is, what if you were to add a new reaction to your chemistry scheme? In this case, we're having 2 new chemical species, Alice and Bob. We're adding them in, so we have to work out how to move these new species around and how we tell the model to move them around. We have to put emissions of Alice in, so we've now got some stuff that's going on and coming into the atmosphere. We put this reaction in at the top, so now we can convert Alice into Bob. We're also forming a secondary organic compound that couples to the aerosol scheme, so we can see the impacts on the aerosol. We're putting in some loss processes, some kind of dry deposition, so kind of falling out of the atmosphere, or wet deposition being rained out of the atmosphere for Alice and Bob. And this is broken down into 10 tasks as part of the training. So some are longer and shorter than others, but essentially this sounds rather simple, but one big complicated task really, and it teaches you how to, regrid emissions files, add these into the model, think about how you output things from the model, how you process the output using Python. And at the end of it, it should cover, 80 to 90% of what most new people want to do with UKCA. And if it doesn't, it makes them a lot more confident and comfortable knowing where to look in the code and in the Rose graphical user interface for where things are. And in the past, we've always made use of Archer to do this training. We make use of the NCAS Puma service, which is a kind of server that's based in Reading. We've held it every year in January since 2013. We've had about 120, 130 people come from all over the world. So it's not a lot of people every year, maybe 10 to 20 at most, mainly from the UK, but a few from New Zealand and Australia, South Korea and other places. And this is some photos taken by our photography department in chemistry of the computer room. Everybody looking happy and engrossed in their work. And as I said, NCAS provides support for the UM on Archer. It also does this now for Archer 2. And this always seemed like a good place for us to run the UKCA training. We didn't have to do any of the setup work to get Rose and Silk and FCM working. It was all done for us from the point of view of users of UKCA, and also had the kind of added benefit that students could get used to using Archer, because often, they might have only just started a few weeks or months earlier, haven't really used the model that much. They get using the HPC, they kind of get familiar with the environment and those sorts of things. However, actually, this system isn't that great. Compile times on Archer for people that used Archer, they were very long. This is usually okay if you're just going to be compiling the model once and then running it for a 30, 40, 50-year run. You leave it for weeks and then come back to it. But the point of the UKCA training is actually there's a lot of compiling that goes on. You're editing the Fortran quite a lot, and you often waiting. What's the error going to be? And so in that sense, you can't wait an hour for your code to compile and then come back to it. You need to get it done in a short amount of time because these courses are only a few days long. So I had to kind of hack in what I call a manual compile. I had to kind of get the students to learn how to compile on the command line for the which was a little bit tricky to work it out in such a way that it still was comfortable for them to do. There's also lots of different user accounts and servers that people are using, and I'll discuss those a little bit in more detail later. And this often led to lots of setup and confusion, and this meant that, the difficulties the students were having, especially at the start of the course, weren't actually to do with using UKCA at all, but we might spend the first afternoon just trying to connect to Archer and get people used to using it. So this is kind of the workflow of what this training was like. You'd come to Cambridge, you'd get a login for your desktop account. It was, a random computer you sat in the computer room, and everybody had their own username for it. So it was shared. But before this, you had to have an account on the Meta Office Science Repository Service where the code is held. This would be in your own name. You'd have to have an account on the Puma server that's in Reading, and this would be in your name as well, but it would be a different username than on Moz's. You wouldn't be using your own Archer account. If you had one, we'd give you a training account because this worked with the special queues that we used for the training course. And this meant that we had 4 different logins to require these different services, and 2 of which were provided on the day of the course. So it was very confusing. People would get the wrong username put in different places. And in terms of kind of planning for running this course online, when we ran it in person, with me and a few demonstrators could run around the computer room and solve these problems. It was we could do it kind of with the student and get them to understand what was going on. It's much harder when things were kind of remote. We had additional problems with the Archer to Archer 2 transition. So we were moving to this new computer. We weren't sure whether Archer was still going to exist when I was planning for this training course. In fact, I don't think it did exist when we ran it. And of course, there was the 2-factor authentication that came into Archer, I think a couple of years ago now. which made it even more complicated for people who weren't sure what they were doing to get onto the system. So all in all, I wasn't particularly happy about trying to run a course online with this, with kind of all these problems. But one other thing I had been doing for a few years as kind of a little toy project is to work on a virtual machine implementation of UKCA. So the Met Office had a kind of sort of supported way of running small versions of the unified model on your home PC. So this was essentially what was needed was to be able to install these Rose, Silk, and FCM packages, deal with all the dependencies, and then you could just use GForce to compile the and for historical reasons, it was set up using Vagrant and VirtualBox. I've since actually ported it to AWS, which was done a few months ago. And you can see the virtual machine on GitHub. You don't actually need an account on the Met Office Science Repository Service if you just want to have a look at FCM, Rose, and Silk. But if you want to run the you need to have an account on Moz as well. And I wrote this up a few years ago, kind of describing using the virtual machine for training. And I originally thought about, well, you can use the virtual machine for training if you're not able to attend the course, and you can do it on your own kind of local PC, but you can come to the course and use Archer, and you can do the training with us there. And because we were going online, we could use this virtual machine for everybody. But I think, getting people to set up the virtual machine themselves isn't really feasible. I had to kind of put it somewhere else. And in terms of what we've kind of done to get this this model to run on the virtual machine, we've basically cut the resolution of the model down. We've cut the top of the atmosphere off. We turned off all the diagnostic output. And so we've gone from a kind of climate resolution on the top row here to a kind of VM suitable resolution, which is much lower course to resolution, and we can run it on 2 cores and 6 gigs of memory, which is perfect for kind of running on most home PCs. But we need a lot of setup to actually get to the point where you can run the You've got to set the virtual machine up itself. You've got to install lots of input files. You've got to kind of run through what's called the Rose stem utility, which is a kind of automatic way the installs itself and kind of tests itself. And this was quite a lot to ask the students to do. And also, that the system I had to run this on, I didn't have AWS at the time, was the Jasmine Unmanaged Cloud, and this doesn't have a Vagrant plugin. And I'm very grateful to Richard Smith at the Centre for Environmental Data Archival, who had ported this setup into Ansible, so kind of all the required packages were there. And I kind of took this Ansible setup that he had, and I've done additional stuff to it. So I've now kind of got it set up to pre-install. So you have to manually pre-install the onto a separate volume and put the required input files in. And then I adapted these scripts so it will now provision multiple virtual machines at once. So we can do all the student VMs in one go rather than having to do them sequentially. We've also got to create kind of login and NFS servers to run this. I'll explain why in a little bit. In fact, I'll explain now. Essentially, we're only given one IP address from Jasmine. So I had to create a login server for the students to come in through. They couldn't go to their machines directly. And if we had the installed kind of on each individual VM, I would have had to go through separately and do this. Whereas what I kind of did was install it on a separate installation on another virtual machine, and then mount that installation via an NFS server. And then the way the virtual machines are configured in the Ansible scripts is it thinks that this installation is a directory called umdir, which is where the exists. And then everything just kind of works magically for all the students when they log in. So essentially with these virtual machines, the students can log in and immediately you can just press go on a job and it will run instantaneously. So without having to do any sort of installation at all. What it also means is that I can keep this installation around and just reuse it again and again and again. And if you wanted to see these scripts, they're on that GitHub link at the bottom there. I've also got a similar GitHub repository for running on AWS using Ansible as well, which I've been playing around with. In terms of using Jasmine itself, we require what's called the J4.small VMs that are there, which are 2 cores and 8 gigs of RAM. a 25 gig volume to install the and all the input files, this server and NFS server and login server. And then for the training that we ran, I used 19 VMs. We had 14 students and 5 demonstrators. Each demonstrator had a VM as well that they could practice on in case a student said, I've got this job that doesn't work, and the demonstrator wanted to take a copy of it. So all in all, it was 42 cores, 172 gigs of RAM, sorry. And as I say, we can install the data volume, and then I can just leave it around, and I can spin up VMs as required. So in fact, I've still got that data volume from earlier on in the year. And if I needed to set up the training again, I could theoretically spin these VMs up and run a training course pretty quickly. Because people are coming from their own personal machines, it's not like the Cambridge desktops where everybody was logging in via Ubuntu. So I had to kind of cope with people coming in from different operating systems. And one of the systems that the CEDA recommended to use was something called X2Go, which uses NX to allow you to connect to kind of a full desktop environment. So this is what you can see here. You could kind of just make out I'm on my laptop from the macOS toolbar on the side. But this is running the LXDE window manager, and you can see that there's a kind of silk window at the front. There's the rows name list at the back. I've got a couple of terminals open with Python and kind of looking at the UMs it runs. So that was available for all operating systems. For people that didn't want to use that and just wanted to come in through a terminal, you could use MobileXterm on Windows or the Mac and Linux terminals to get in. And all this, I tested all this. I actually had a kind of pre-event from some students and postdocs in Cambridge, kind of logged into one of these machines and tried out various things and debugged the system for me, which I'm very grateful to them for doing that. And all in all, it took about 6 weeks to kind of go from not having anything to having a kind of working system where I could run this training on. And actually what this has meant is that the workflow is far simpler running it in this way than running it before. So everybody has their own personal computer. They know their login details for that. They use it every day. They've got their own Moz account, but then, that's their own personal Moz account. They may be using it before. And if not, that's the only thing they need to know the username for. The way the virtual machines were set up is that I provided an SSH key for them. And I made it so that each virtual machine, so each machine was numbered sequentially from 1 to 19. And the usernames, I kind of made usernames for each one that was also similarly numbered sequentially 1 to 19. So if a student says, I've got a problem, all I needed to know was what their username was, and I knew what virtual machine they were on. And just made it easier for them to kind of debug issues. And I'd made an admin account as well, so I could SSH into each of those virtual machines, and I could take a look at their output and be a virtual looking over their shoulder to see what was going on. So I say there were 14 participants. We had 5 demonstrators, and we had 3 or 4 demonstrators at any one time. This is a nice group photo we took rather than a kind of in-person one. So it was quite good, and I think the students got quite a lot out of it at the time. I had to change how the days were structured. So previously, we kind of just worked in a computer room, worked through the tutorials, and people could go at their own pace all the way through them. Some people would be, could finish rather quickly. Other people, still hadn't quite finished by the end of 3 days. We tried to structure it a bit more and also tried to minimize the amount of Zoom that people were going to be using. So we asked them to kind of read through a lot of information at the start. We had videos from previous training events, lectures from when it was supported by NERC, and we had a whole week. We got people to connect to their personal machine a day or two before, and they asked them to actually work through the first 2 tutorials, which are rather simple, so that by the time they kind of started, we could just debug any final issues in the first morning. And then we only had 2.5 hours of Slack, of Zoom a day to try and minimize Zoom fatigue, breaking things up with kind of lectures in the morning, welcome and get everybody to introduce themselves. We also use Slack a lot to provide kind of text support outside of these hours, which worked really well for the training. One thing I did do before running the training was I asked the RSE Slack if they had any suggestions for running online training events, and they gave some really helpful suggestions, which I tried to incorporate. and I tried to put in a difficulty rating and a kind of time to complete for each of these, from estimating how long things would take to make people kind of more aware of how far through they were for this training, because we're in the middle of the third or fourth, which are pretty hard. When you get to four, you could feel like there's a long way to go, but actually things get easier after that point. Put a lot of information on how to connect. I did overview videos kind of for the whole thing, which I would usually give in person. Recorded that and put that on a YouTube channel that they could watch as well whenever they wanted. And all this was kind of updated from how we did this previously. In terms of the feedback we got, we were really pleased with the feedback that the students said for the training. So everybody pretty much felt that they had more knowledge and skills on UKCA from before the course, and that people were extremely likely to recommend this course to someone else. And although people were enjoying it, everybody did say they would rather have attended an in-person event rather than an online one in future, which is definitely something to think about. In terms of Slack, we tried this in previous years and we'd had basically nobody using it at all. But that's when everybody was in the same room and was mainly just talking with the person next to them. Everybody was separated. Now we actually had a very active Slack channel. Nearly 300, I think, different things were raised and talked about. We even had students helping other students on Slack, so it wasn't just me and the demonstrators. And one thing that the RSE Slack suggested was to have a kind of private demonstrator channel or way of communicating, which was really helpful. So, I could say a message, could somebody come into Zoom breakout room 3 and help somebody there on this thing and that sort of thing. So that was really good. Slack again was found helpful and was easy to use. And I was really interested in how people thought about this virtual machine setup. Actually, the majority of my time prior to this training was setting up this virtual machine system, coming in from lots of different operating systems, and everybody said they found it easy to use. Absolutely everybody. There was one person that had minor difficulties with copying and pasting text, but everybody else didn't have an issue. And this is compared to using Archer, where as I say, you might spend a whole afternoon debugging how you get onto Archer, whereas this just almost seems to work seamlessly. So what I found from this is this cloud environment is excellent for running these online training events. And I think even for online, when we move from online to in-person courses, I think I'd like to keep doing it in that way. It was so much easier for everybody. It was a lot of effort to configure these virtual machines though, but of course once I've done that, I can use it again, and the students found it a lot better than using the Archer connection. Slack was actually used, certainly in this online event, course, and the feedback was all positive, although, as I say, people would have preferred an in-person course. I think it was much better to respond to kind of people's problems when it's in person. It's a bit different when you've got a kind of Zoom environment. Thank you.
Brilliant. Thank you, Luke. We do have a few questions for you on the Slido. People want to put any more questions in? Oh, there we go. Excellent. And feel free to upvote them if there's anything that you're particularly interested in. I'll go through them according to the votes. There we go. Okay, we'll go for the top question. So first question, that's a lot of dependencies you mentioned at the start, organically grown over time. What's the cost of managing these versus the cost of modernizing things? So you've got Python 2 and Python 3, Git.
Yes. So, I mean, I'm not in charge of that. So, the Met Office, I'm not in charge of whether they use Python 2 or Python 3 and Subversion versus Git. I mean, the Subversion thing, they moved to Subversion many years ago. I mean, I think they were moving to Subversion when I started in Cambridge 15 years ago. So, they kind of moved there before I think Git was really as big as it is now. In terms of Python 2, Python 3, they are rewriting everything in Python 3, and it's taking a long time. And I think so, especially something like Silk, which is coming from Niwa, they're not just kind of doing get exactly the same functionality. They're trying to do lots more new things, which is mean it's taking even more time. I mean, we installed the on the cluster in Cambridge, and I'm sure the RSEs would tell you that it was a right pain with the dependencies and to get it working. And so I sympathize. I wish it didn't have these dependencies, but unfortunately it does. And it is quite a lot of a cost. And the Met Office are aware, but they are it works in their system. You know, the Met Office system, actually everything works seamlessly. So there's less of an impetus for them to change things compared to us on the outside, where we're going from, you know, a server we own in Reading to a server somebody else owns somewhere else, that sort of thing.
Okay, brilliant. Thank you. Next question. Do you think you'll get a problem transitioning people from the cloud environment to Archer?
I mean, in terms of the training, I'm not sure I'm going to go back. Personally, I think in terms of people transitioning from the cloud to Archer for their own work, I mean, that's a different thing. The suites are much more limited in terms of usability, so they kind of have to go to Archer if you wanted to run any sort of proper climate runs. You know, the suites are cut down heavily. I mean, you could run, if you had the costs, you know, you had the money, you could run on AWS or something, one of these really big jobs. But it's still cheaper to run on the bare metal machines than on the cloud, I think, at the moment. I mean, it's a different thing. I think that the focus on the training is much more on how fast you can compile and see the errors. And they might rather work on a cloud or a virtual machine, and in fact, they still can. So we do have students, certainly in Cambridge and other places, who do their development work on their own personal virtual machine, get it all debugged and running, and then only move to using a HPC when they know the code can compile for the most part. So, you know, actually that's quite good. You know, this system is being used not just for training properly, it's being used for development as well.
Okay. Excellent, thank you. A question about your students. Did they all complete the prep work that you set them, or did you need to hassle them to get them to get on with it?
They'd all tried connecting to their machine, I think. They didn't necessarily read all the things, but actually it was okay. You know, it wasn't too much of a hindrance. I mean, ideally, this course, there were other courses NCAS cover on the UM, and ideally, you would have had everybody attend the UM training course a few months before the UKCA training course, and that never happens because people only, you know, a lot of people just come to the UKCA one because they don't think they need the UM one as well. And so actually, I'd kind of written the training to be, you know, it's a really steep learning curve, but I have had people come on the course who've only ever used Windows and never used a model before, and have actually been able to get a lot out of it relatively quickly. So, you know, I'm used to them not completing the prep work, and that still kind of works out.
Okay, brilliant, excellent. Next one, would it be possible to leave a one user sandpit running online permanently so that people can learn at home at any time?
I mean, that's partly dependent on Jasmine being nice to allow us to use that resource all the time. They allowed us to keep one of the virtual machines up for one of the students that was that hadn't quite finished, and I've still got that tendency. I can still spin things up if I need to for testing, but I know that resource is a bit limited. As I say, I have ported it to AWS, and I'm looking at the moment to try and provide a kind of virtual machine image there for the EC2 instance that then people could take, and of course then the charging would be done by their own AWS account rather than from us for them running it. But there are licensing issues with the UM as well, so you have to have a kind of you have to sign the license or have an account on Moz to be able to use it. And it's not something I can kind of provide to people for free. They have to kind of go through some sort of process to get onto that. But you know, anybody can spin this virtual machine up themselves if they have a spare 8 gigs and a couple of cores on a server somewhere, and you're allowed to use VirtualBox and Vagrant. You can spin it up yourself, and within a few hours you can be right up and running as well if you follow the instructions, which are relatively clear.
Oh, cool. Excellent. And a final question, did the students tell you why they preferred in person? You know, if online was the only option, would they still come?
We stupidly didn't ask why they preferred, why they preferred. We didn't say, and you know, what would you prefer and why, which we probably should have done. So I'm not sure. I mean, I think certainly from my point of view, running it's much easier to interact with the students and talk with them, and you know, perhaps they're aware of that as well. I mean, it did allow people to come internationally. So we did have one person from Sweden dialing in. Most of the people were in the UK at that time. In terms of would they still come? I mean, they've come in previous years. Sometimes it's not been that many. Sometimes it's been, 22. I don't know. We'll find out. I mean, I think the other NCAS courses, partly because this one was successful, have done some online for their other kind of computational training courses. We'll see what happens in the coming months as to whether I run it online again or not. And we'll ask that question this time.
Excellent. Thank you. Well, thank you very much, Luke. That's all the questions, and thank you everybody for your questions. So we'll now move on to Ben from Swansea. So same as me. So welcome, Ben. Over to you.
Hello there. I am hoping that A, you can all hear me, and that B, everything is working, because Zoom is being a bit silly, so it seems to be quite slow to respond to things. So hopefully you can all hear me. Yes. I don't know how I can. People let me know if you can hear me.
Everything's fine for me.
Excellent. Good to know. Right, that's a good start. So yeah, I'll just share my screen, get this all set on going. So share screen, and I want to use that one there. Yep. Okay, if everyone can see the current screen, yeah, it's good. Right, so obviously, hello, I'm Dr. Benjamin Thorpe. I work as a research software engineer for the Swansea Academy of Advanced Computing, based out, as I've already said, at Swansea University. I want to start by saying this talk was originally written with a more technical audience in mind. So you'll notice the title has two parts to it. It's the really technical, boring bit of compartmental modeling for spread of everyone's favorite virus. But also we've got, I also thought this audience might want to know more interested to hear about my experience of learning a programming language during a national emergency and working on a project to do with that. Because I had the project required R. I've never used R before. And I admit I was a bit apprehensive, but I think it worked out okay. So we will see on that one. So hopefully I can skip forward to the next slide now. Yes, I can. So the story so far, then, we'll start with the story. It's early 2020. A certain well-known virus by now starts spreading across the globe and is reaching into the UK. And after a bit of umming and ahhing, it was decided that Wales urgently needed a way of tracking and spreading and predicting the spread of COVID-19. And as part of that, the Welsh Technical Advisory Group, who are the advisors to the Welsh Government on matters of science, approached SA2C and Professor Mike Gravener at Swansea, who is an epidemiologist, to undertake this work. Now, I didn't join this project from the outset because we already had an experienced R programmer on our team. However, he then announced that he found a new job. Nothing against the guy for that, but it put us in a bit of a mess. So I would ask, would I be able to join the project? So now, at the time, I'd never used R, and I was an experienced programmer. I'm a background in C, C++, and Fortran, and but it was a new language to me, so it was a bit of an ordeal. I'll admit I was apprehensive also because epidemiology is not my background. My background is physics and engineering, so it's like it was a completely new background, a completely new programming language, and it would have been it involved a lot of new experiences. So I was a bit apprehensive, but hopefully I took the job on anyway, and we will see how I got on. So a bit of a background on what the model we're using was then, because it was already a pre-existing model, and it was the LSHGM model is developed by the London School of Hygiene and Tropical Medicine. It's written as a package within R. So it's actually the underlying model is written in C++, and then R is used to interface with that and to handle all the data wrangling, all the bits and pieces, and do all the plotting. So it's an agent-based SEIR model. I will get onto what that exactly means further down the slides, but and it was initially built to stimulate spread of infectious diseases across the UK, and this is a generic model. So, however, we had to adapt it to A, work with COVID-19, and then B, actually specifically look at the impact across Wales. So we eventually developed a model, and we now have a model that can do track spread of COVID-19 across local authorities and even health boards within Wales. And it takes into account various different things like vaccination, variety of different lockdown strategies, school closures, etc. So, if we're right. So at this point, I want to break into why do you use R? What are my thoughts on this? And I've decided to come up with a bunch of. I have a few pros, a few things I like, things I don't like, and then a few things that I've learned to appreciate. Let's say. So we'll start with things I like, the good things. It has data frames natively. For those who don't know what data frames are, they're actually very useful. It allows you to take a bunch of different disparate variables and data types that are all linked to something. So in this case, we have we want the number. We want to have a data frame that contains a whole bunch of different variables that are all linked to a person in our model. So it might be the current infection state is their age, their and things, and you can. A data frame allows you to tie all those together, and there can be different data types, and there can be different data, different sizes, different lengths, and it basically works like a mini database, and you can do things like filter out various things you don't want very efficiently. And other languages do this, but R is great because it has it just built in natively, and that's if you're into that kind of stuff and using big data, R is a good choice for that purpose. There's also a lot of well-optimized packages in R for scientific use, things like PLYR and Tidyverse, which do data frame stuff. You've also got ggplot, which is a great package if you want to plot data in any which way you can think of. And you've got things like fir and purr, which are for parallel processing, doing data, all sorts of crazy things. If you can think of something, there's probably a package for it that will work. Also, it makes you popular with pirates, which is always just a good joke to land on, because making new friends is important. So, what don't I like them? R is a memory hog, and people told me this when I started, and it's true. The way R uses data structures is not the most efficient, and it might only seem small at the start, but it soon compounds. We got to a point where some of our data just wouldn't fit in RAM on any machine I had. And I have a 64 gigabyte machine, and it wouldn't fit in RAM. So we had to do some tricks to get around that. And fortunately, data frames exist, and you can use it for that kind of stuff, but it's less than ideal. Also, being an interpreted language, that makes it naturally slower. There's not a lot you can do about that. That's just the nature of the beast. There are many pros to interpreted languages. Some people hate them, but I personally, I'm not a big fan. Fortunately, though, you can tie into compiled languages, so you can get a bit of speed boost that way. Finally, on the con side of things, it gets dependency, what I call dependency rot, and Python has this as well. When you start relying on so many packages to other people and dependencies to other people, you can get into a situation where everything a developer somewhere changes something, and your code just immediately breaks overnight, and you've got to fix that, and that takes time, effort, and resources, and it's not pleasant when it happens, but it's unavoidable. But it's one of those things that you sort of have to be aware of when you're dealing with it's the nature of the beast, really. So I put in some neutral points as well, which these are things that I've learned as I was going, and I now appreciate why they're there, but at the time they were annoying. So type handling and variable scopes are both unconventional in R. Type handling I actually quite liked when we started, because unlike in most languages, you can, if you say x equals 5, it doesn't matter if that 5 is an integer, 64-bit, 32-bit, doesn't matter if it's a floating point number, doesn't matter if it's literally just string 5, R will handle that, and R will convert it accordingly depending on what you want to do. A great example of this is you can use the plus operator, which is either add or concatenate, depending on what you want to do. And you can use that with true plus ABC, a string. Now, in any other language, the language will go, what the heck are you doing? You can't add a logical to a string. Now, R will go, well, true could either be a logical, or it could be the literal string TRUE. And it will just do that automatically. It will wrangle the data types round and so you can just do TRUE, ABC. It was concatenated too. That's great. On the downside, when you're moving into things like compiled languages and you're trying to interface with all the things, R can do crazy things with the variable types, and that can catch you out. It did for me, where I didn't realize it was converting an integer into a floating point value because we're using it somewhere else. So it's not a terrible thing, but when you're using compiled language, you have to make sure you specifically say to cast it into a certain type so that your language is happy with it. And you have to make sure that you know what type comes out of the back of the language for the same reason. So it's a bit more work, really. It's not a terrible thing. It's just it's a bit extra work that I could do without sometimes. I also come to variable scope being unconventional. That's another thing that screws with me a bit, because in most languages, global variables are devil's work. And whereas in R, global variables are norm. If you're starting R, you start off your program, everything's in global space. So you define y equals 5, that variable's y variable is now a global variable equals 5. And then you move into a function, and a function has access to function variables and global variables. So it has access to the y equals 5. If you then define another variable x equals 6, it will have that in the function space. And you have to be aware that these two things exist, because you can't access function variables outside of functions, but you can access global variables anywhere. And this moves up my last point about assignment, which is what this business here is. For those who don't know, these monstrosities, as I described them, are the assignment operators. You can either use equals, you can use this left angle bracket dash a right angle bracket and dash, or you can use two angle brackets and a dash, either direction. Now, when you first see this, it drove me mad because I was like, why are people using these? What do they mean? What is going on here? And it took me a long time to appreciate why they exist. The reason is equals is valid for an assignment. So x equals 6 is a valid statement in R, but it's ambiguous because if you put x equals 6 on a line its own, that's an assignment to a global variable. If you put it in a function or you call to a function, you're defining what you want the variable to be inside the function. You're not defining it in global space, and that can catch people out. It's ambiguous. So R decided to use these assignment operators. So the most common one is left angle bracket plus dash. And that just means assign everything on the left-hand side of this to this variable then. So you put x, left angle bracket dash, and then everything beyond that is 5. That assigns x equals 5. You also have the opposite. You can do the reverse of that if you want, where you can put it the other way, which I don't understand the logic of, but never mind. That's a slight bugbear on my part. The reverse is also true. So you can have it 5 dash right angle bracket x, and that will do exactly the same. It'll do x equals 5, but it'll do the reverse. I don't know why you'd want to do that, but some people do. There is also this double business, which is actually really useful. If you need something to be a global variable, you can just do double angle brackets dash, and it will go, okay, that is definitely a global declaration, and that is even inside a function. So it means you can access and change global variables unambiguously and not cause any problems, assuming you know that is the thing it does in the first place. As I say, I put it as a neutral point because I'm used to it now, but when it started, it was drove me insane because it seemed so archaic and strange to have these weird symbols that mean the same thing as equals, but don't always mean the same thing as equals. So I thought I would bring it up as a point. So back to the model then. So I said before, what the heck is an SCIR model? Well, in general, an SCIR model is simply a way of tracking a disease through a population. So you start with a population of susceptible people. Let's say you've got 10,000 people and they're all susceptible. So you put them all in this bucket here, S, which is there. Bucket there, S. You then have 4 other buckets. You have exposed, E, infectious, I, recovered, R, and death, D. And as you move through each time step, your people move from get exposed to the virus. They move through. My camera's just turned off. That's not very helpful right now. Not very helpful right now. Hopefully it comes back. If not, no worries. It's back good. So as you move through the disease, your second will get exposed to the virus, move to exposed. They then, after so many days, move to infected. After so many days, they'll either die of the virus, they'll deaths, or they'll go into recover from the virus, and they'll go into here, and they're no longer infectious, no longer involved. There's also a path backwards, which allows you to have waning immunity. So you have people go from recovered back to susceptible and continue this loop. This loop continues until either everyone's dead or time ends, which is quite sad, really, but that's the way it goes. So from this, there's also other ways into this. As you can see from the model here, we've got things like natural births, natural deaths, and you can add these things in. Our model doesn't use these because we don't run over a longer period of time, but they're there for, on the general case, you'd want them there. So that's a pretty good expression. So a little warning now, this presentation contains maths. Now I'm aware that this is a more general audience and I really cut the maths down, but there's some stuff you have to have in here to explain it properly. So I apologize in advance, and if this works properly, I'm going to put some puppies in the corner as an apology from me. Hopefully you can all see that. And yes, with the maths on the screen, there will also be puppies on the screen to hopefully curb people's anxiety as we go through. There's not a lot of maths, but there is some maths, so just to warn you. So here we go. The model itself is actually mathematically quite simple. It's surprising. When I first saw it, I was surprised, actually. But it essentially boils down to the solution of 4 differential equations. And these are the equations you want. So you basically got how the rate of change of S, rate of change of I, rate of change of E, rate of change of R. And essentially, you've got a load of parameters you can play with. You've got birth rate, death rates, various different contact rates, all that jazz. And all you need to know is, realistically, you're solving those 4 equations. Each time step, you're going, how many people do I need to move from S to E to I to R? And so on and so forth. And how do these all interact with one another on a mathematical scale? So yeah, remarkably simple maths, but it has to be said. There's also this important parameter, which is R0, which is the reproduction number. You may or may not have heard in the news, this number, it tends to get quoted a lot, which is, on average, how many people does one infected person infect? each day. So one becomes, if one person infects 3 people then go and infect 9 people. I can't remember the numbers exactly, but that's basically how it all works. And it directly affects how quickly the virus spreads and how fast things go out of control. So it is important. But right, so moving on. So we've got I'll get to the copies now because we don't need them now. We've got the advanced SEIR model. Have I gone forwards then? Yeah. So we've got a bit more going on here because our model's a bit more advanced than a basic case. So there's a few more extra compartments just for mostly for convenience for tracking things better. So in our case, the extra thing you need to worry about are we've got vaccinated compartments. So you've got susceptible vaccinated, recover vaccinated, which you go in and out of based on waning immunity and things. I will go into how vaccination works on a separate slide, but they are there for completeness. You've also got your infectiousness becomes split into 2 parts in our model because we have asymptomatic transmission in our model. So it means that some people are actually asymptomatic, and that causes problems. So when you're exposed, when someone is exposed to the virus, they go through. It can either become asymptomatic or symptomatic. If they're asymptomatic, then we say they're half as infectious as they would be, but their contacts don't change at all because they don't know they've got the virus. And they then travel through and eventually recover and eventually go back around loop. Symptomatic cases are a bit more complicated. They involve what's called preclinical, which basically means that they're not hospitalized, but they have symptoms. We assume that they will be self-isolating, so they've got lower contacts, but they are infectious still, or very infectious. So they can go one of 2 ways. They can either go average of 5 days, back out of the loop, back around the loop again, or they can go spend 1 to 5 days in this section and then go to the hospital. Hospitalization, we split into 2 because governments like to know how many ICU beds versus non-ICU beds you're going to want because it's a cost thing more than anything else. Obviously, an ICU bed costs a lot more and has a lot more resources involved than a non-ICU bed, so you need to know the difference. So we've got two different boxes here for this purpose. So you can see that, and again, you can either get better, recover, you can move between the 2 of them, so you can get worse, go to ICU from non-ICU to ICU, or you get better into hospital and then out again, or you can die, as exactly as indicated there. So if we move on, so estimating the contacts now. So each agent in our model can be one of 16 different age groups. So this allows us to change how the contacts work depending on how old they are, how old the person is. Because young people, children will be at school most time, adults won't be. Will be at work. The elderly will probably won't be either, and they'll be off in the coffee shop or something. So everyone has different rates of contacts based on their age. So each time step, we say how many people are infectious, and we select each of them gets R contacts, which is just a number that we decided based on how infectious the virus is. Each contact then has a random chance to be one of 4 contact types, which are school, work, home, other. And each category of these types has a matrix that defines the probability that the contacts will be infectious based on both their age and the age of the person they're talking to. So, so if, for example, if a child meets their grandparents, there'll be a different probability that the transmission will occur versus a child meeting their parent or meeting a random stranger in the street. So it's that kind of stuff going on. In this case, the matrix is just a grid, and you get rows which indicate the age of the person who's infectious, and you get columns that indicate the age of the person who is susceptible, and you just pick out the number you want in that grid to give you the probability that you'll cause an infection to occur. So how do we, next step is how does it account for lockdown measures? Well, basically we define we multiply our 4 contacts by a factor that says how will those contacts drop based on this measure. These came from Mike's intuition and experience. He basically, I wouldn't say guessing, it's educated guessing, because we say, we think closing the shops will reduce contacts by 60%, so we'll drop all the contacts by 60%. So homework, we get one factor that affects them all. For this case, in this case, school gets a separate factor because that's a special case. It either is 0 means school closed, 1 means schools are open, and we can have anything between for when the Welsh government wanted to do partial reopening, so we had 2 or 3 years back, so we had 20% of the kids back. We had it on a varying scale. There's also another special factor that gets multiplied. For anyone over 70 gets the elderly factor, as we call it, which is the advice to start shielding. So they get I think it's 20% bump down on the contacts once shielding was officially announced. So that stayed in for a while. So yeah, that's just there as a part of the model as well. So I said the total vaccinations, and I will. So
Ben, are you going to be able to bring this in the next couple of minutes? So we've got time for some questions.
Yes, we shouldn't be too long now. I'm quickly skipping through this lot. So yeah,
thank you very much.
A bit over time. So yeah, vaccinations works by simply saying we have so many vaccinations per day, and we take that many people out of the model, put them in SV or RV, and then they're no longer involved. After so many days, WV in this case, we can take them back out of the model and move them back and forth. And we have a certain efficiency, so we say we pick out 100 people, and 60 of them will their vaccination works. 90 don't. So that's easy enough. I'm going to try and spin through these now. Bit of post-processing stuff that we have to do because the vaccines are only a single dose in our model, and the real ones are 2 doses. And B, there's we also have different effectiveness based on not just on transmission but on infection, on hospitalization and death. So there is some maths there, and there's some puppies there as well. But as you say, I'll let you. The slides will be online because it's massively complicated now, and I want to try and get through this because I'm running short on time. So why is that changing my camera going? I shouldn't do that. So variants, main presentation there, right? Variants. Annoyingly, the virus mutates, so we had to change for variants. In this case, we just had an extra factor we put into the contact rates to scale it up or down in order to introduce new variants at different times. So we have an alpha variant in January, and we had the delta variant in June, which we had to account for. So quickly how we get onto Wales. The simple put is we have 22 separate groups in our model, 1 for each local authority. We use census data from 2010 to get the population sizes, and then we using the case data from the first wave in that early March. We had an initial seed, which is the number of people we want to move into the I immediately to get things going, and we set R0, and then we aggregate over all the compartments to get the dynamics over the whole population. There's also, for more localized stuff, we eventually needed to move to health board level because the NHS divides England and Wales into health boards, and Scotland, I believe, as well. So we had to work out how to do that. And it turned out the easiest way of doing that was to have separate models for each one, because it turns out that they don't map to local authorities anyway. So in the end, we use separate models, all with seeded the same way. So we ended up with 8 different models, one for each local authority, one for each health board, and one for on the national level. So a brief look at the data here. You can see the kind of thing we get. So in this case, we've got the black dots are the real world data, and the lines are the various different variants that we have going through. Apologies, these are not particularly well colorblind suited, but it's hard to get five colors that work with colorblind. So I've done my best. But as you can see here, we've got we start off in the original variant, we go down as the lockdown kicks in, after Christmas, and then you see there they split into 3 variants there, and then they split again. At the time, we didn't know how high Delta was, so we split into 3 and said the upper estimate, lower estimate, mid estimate, and we can see there we split off, and we're tracking the middle estimate there. I think we still are, to be fair, but quickly, you can also get out things like number of deaths. Again, we track quite well, number of people in wards, how full are the ICUs getting, how full are the wards themselves getting, and that's it really. So it was a bit of a rush towards the end. I got a bit carried away with the R section, I think. But does anyone
thank you very much, Ben. That was much appreciated, and I do wish you had more time. Actually, I'm close to home this one. Right, yeah, I'll kick on to the questions quite quickly there. So question number 1: have you tested the reproducibility of the model? Is it publicly available, and is it documented?
The exact version we're using is not publicly available. The basic version, I believe, it's a bit of a strange one because we have a slightly different version. It includes some closed source code, unfortunately, but The main model is, I believe, there's a version 1 is publicly available, I believe. We're using version 2, which is slightly more advanced. I believe it's called COVID-M if you want to try and find it.
Okay, and it looks like somebody's been looking at your data. So why does alpha resurge in 2022?
It's because that line is more because that assumes alpha was the only variant there. And in that case, we were opening up, the whole lockdown would open up at the end of August. So we just go, there's no more lockdowns anymore, at which point the alpha variant resurges because it was spreading quite rapidly. If we go far enough in time, the original variant will start respreading as well. But that took a while longer because of vaccination more than anything else. But yeah.
Okay. Thank you very much. I think I'll skip the rest of the questions in order to get us some time back. Could we have, say, would a 3-minute break work, Chris? Right, so we have a 3-minute comfort break. I'm back here in 3 minutes to carry on with the next one. Hi everyone, welcome back. I hope you've had a chance to have a stretch your legs and that kind of thing. So without any further ado, I'll pass you over to Oscar. Oscar.
Good afternoon. I'll just share my slides. Excellent. Can you all see and hear me okay?
Sounds good to me.
Excellent. Okay, I'll get started. Okay, so good afternoon. Thanks everyone for joining me today. So I'm Oscar Giles. I'm a research software engineer at the Alan Turing Institute. And today I'm going to tell you about Project Odysseus, which was a multi-institutional collaboration sort of homed at the Alan Turing Institute, working with the Greater London Authority, that's sort of the London Mayor's Office, and Transport for London. And this project sort of aimed to monitor busyness during business of London during the COVID-19 lockdowns. So this project involved researchers from Turing, the University of Warwick, UCL, and Cambridge University. And sort of one of the key interesting aspects of this project is it sort of naturally evolved out of an existing collaboration between Turing and the Greater London Authority, which was a project looking at forecasting air pollution in London. So I'll tell you a little bit about that air pollution forecasting project. I'll talk about the data sets and the infrastructure that were kind of underpinning that project. And then I'm going to sort of move on to talking about some of the ways that these were repurposed to monitor busyness during the COVID-19 lockdowns. So a bit of background on Urban Air. This sort of started in 2017. The project was led by Theo de Moulas, who's the sort of deputy director of our data-centric engineering program, and also the sort of lead of Warwick Machine Learning's group. This started as a collaboration with the mayor's office, and the mayor sort of came in on a mandate to try and tackle the sort of London's high air pollution sort of levels. So Theo's team were particularly interested in the sort of complex modelling challenges that come with trying to forecast air pollution. A bit later on in 2019, members of our sort of research engineering group, so myself and my colleagues James Robinson, joined to develop, sort of take the work done by this team and develop a cloud-based system which could then forecast air pollution reliably sort of every day. So quick introduction to the team. We were about 20 strong, mostly sort of researchers collaborating to the project and also sort of analysts from the Greater London Authority. And then we had a sort of fairly small RSE team with sort of 2 of us working there. So our sort of overall aims here were to produce 48-hour forecasts of air pollution in high spatial resolution. So we wanted to sort of beat the sort of spatial resolution of existing models. As an RSE team, our job was really to develop the infrastructure and software to allow us to reliably collect data that's relevant to forecasting air pollution, to sort of build automated data engineering and feature extraction pipelines, and then be able to sort of reliably train our models, forecast air pollution, and then expose those forecasts back to GLA and also to the public via an API. So we can start by asking, well, how do you forecast air pollution? And a good starting place is to measure it. So London has multiple sensor networks. You may have seen these kind of big air pollution sensors kicking around London. It's not always immediately clear exactly what they are. And they sort of come in different shapes and sizes. Often they're near sort of roadsides, but they can also be different locations. And these measure a range of sort of air pollutants. Another source of air pollution sort of monitoring is from satellites. So the European Centre for Medium Range Weather Forecasts provide sort of measurements of air pollution. These are at a much sort of lower spatial resolution, but you can obviously see sort of air pollution moving over a much sort of wider geographic area. Once you kind of know about, once you're sort of measuring air pollution, you might want to know what sort of factors affect how sort of long it stays around. So one of these bigger factors is sort of land use. So you might care about things like where your road network is. You might care where sort of bodies of water are, where vegetated sort of green spaces, and in particular, you probably care about buildings. So how high are they? How close together are they? What's their kind of orientation relative to each other? Yeah, I mean, a lot of fun making these figures. You also are going to care about weather. So you want some sort of weather data because air pollution behaves very differently when it's sort of wet, cold, and windy compared to when it's a sunny, hot, still day. And then finally, you probably want to know about where pollution is coming from. So in London, one of the largest sources of air pollution is traffic. So if you know where all the sort of cars are, you probably have a good idea about where pollution is going to be. So we on this project, we had access to 2 sort of key data sets, which we got from Transport for London. The first is Transport for London's Scoot network, which consists of about 12,000 in-road sensors. That are spread around London, and these basically just count vehicles as they drive over the top. And this system was developed initially to control traffic signals. The other sort of source of information we have is from TfL's traffic cameras. So they have a lot of traffic cameras, and the data feeds for these are sort of publicly available. So we can sort of use those to monitor traffic around the city. So once you've got your data sets and you've got all the ingredients, you can do some feature extraction, train your models, and it turns out it's actually quite a complex modeling problem because of the various spatial temporal sampling resolutions that you have, these different noise levels in our different data sources. So this has kind of been this focal point of our Warwick machine learning team. And then now we're at the point where we can start forecasting air pollution. We need our system that can reliably do this every day. So we built a sort of cloud-based solution on Azure, which has sort of been generously funded by Microsoft. At the heart of it is a Kubernetes cluster, which runs basically all of our jobs on the system, from data collection, our feature processing, actually fitting the models themselves, and also hosting all of our sort of web APIs. We then have a Postgres database for storage, and we also use that for processing a lot of our geospatial data. And then a nice thing about our sort of setup is everything's kind of deployed via Terraform. So for those unfamiliar with Terraform, this is a tool which allows you to sort of describe all your infrastructure as code. We also describe all our sort of cluster configuration with Helm, which means we can kind of redeploy our infrastructure in no time at all. So we were kind of happily working away on this system. And then, much as everyone's experienced, when the projects were all disrupted, COVID-19 happened. And on the 23rd of March, the first sort of lockdowns came into force. And for us, this threw a pretty big spanner in the works, largely because the teams we were working with at GLA and to a lesser extent Transport for London had a very sort of big change in their priorities. So they immediately refocused pretty much all their resources into dealing with the pandemic and also helping people to sort of get through these lockdowns. And the teams we're working with are responsible for a lot of the data analytics that are used to kind of support the decision-making by policymakers. So we sort of said, well, you know, is there anything we can do to help? We'd love to do something if there's something useful we can do. And sort of talking to our collaborators, they sort of made it clear that they had a real need to sort of understand the busyness of London. So as interventions come into force, are people still staying home? As lockdowns are lifted, are people getting back out? Are there particular areas of London that are particularly busy or difficult for people to socially distance? These sort of questions were really kind of in people's minds. And we thought, well, okay, so we're already starting to monitor busyness in a way. We have access to these different data sets from Transport for London, and we've been looking into using them to monitor traffic. However, we know that there's also information in these data sources about pedestrians. So our TfL traffic cameras cover a lot of sort of pedestrianized areas. What's more, we already have a lot of infrastructure in place that's already plugged straight back into GLA and TfL. So we're providing data to them via our APIs, and we have this sort of scalable cloud infrastructure so we can quickly sort of add new workloads and jobs. And that's really how Project Odysseus came about. At this time, our team sort of grew pretty substantially, and we went from a mostly sort of researcher-dominated small RSE team to suddenly having sort of 6 RSEs, and we had a lot more kind of capacity for our RSE work. So we had a lot of people. We decided to split into various project teams. The team's goals were to build different sort of systems, but often they would sort of share the underlying data sources. So one of these teams was our sort of camera social distancing team, and their task was to analyze these CCTV and traffic cameras. We had a modeling team who were interested in modeling changes in activity levels across London against various baselines. And we had an early warning system team who were trying to work on a system to sort of detect and pinpoint the location, shape, and sizes of clusters of activity in London as they arose. Then finally, we had our RSE team, and so our Turing team was joined by RSEs from UCL and also Warwick University. And our sort of role was to work with all these sub-teams to help them access the data sets they needed, make sure they had the right computational resources, to scale and develop our existing infrastructure to bring their sort of workloads in, help them bring code into production. We were responsible for sort of securing, making sure our sort of APIs were suitably secure, and also to sort of scale these up. We had a particular kind of goal to help these teams maintain a sort of consistency in code quality, and were able to sort of follow best practices. And perhaps most importantly, we were particularly keen to make sure that we could sort of upskill these teams so that they could maintain ownership of their code as it went into our sort of production system, as we knew that our RRC team would be on the project for a sort of shorter time than the researchers. So I can't talk about what all of these teams did and their fantastic work in 20 minutes. So I'm going to focus in on the sort of camera team, one of these sub-teams. So they had a sort of key question, that was to use these traffic cameras to start asking questions like, how many people are there in different parts of London, and are they able to sort of socially distance? These are the kind of grand goals. So the data set they had available to them was this traffic camera data, exactly the data set that we've been using as part of our air pollution project. So if I tell you a little bit more about those, they're readily available at this website. There's a sort of example on screen now. There's 912 of these across London. They're sort of in a very kind of low resolution where it's very sort of difficult to identify any faces. They're sort of quite pixelated. So what did the team do? They took some sort of popular object detection models that sort of trade speed over accuracy somewhat, and use these to detect different objects in these video feeds. So we can detect and sort of locate buses, cars, different vehicle types, pedestrians, cyclists, and they sort of train these models with a custom labeled data set from this our traffic cameras, this DFL traffic cameras, and also with some other sort of closely related transfer learning data sets. So once they kind of had this workflow in place, we're faced with the problem, well, how do we scale this to 900 plus cameras that we have over the city? So these video clips, they come in sort of 10-second batches, 10-second clips. We can shove them into a batch. And then what we really want to do is be able to process these images so we can sort of start counting how many like pedestrians there are in a scene, for example. And we need to be able to process those sort of faster than the time that the batch represents. So if you've got an hour of footage, you really want to be able to process that in less than an hour. And the reason for that is we want to get this data back to GLA and TfL as quickly as possible with some constant delay. And if it was taking us longer than the sort of time represented, our system would be like slowly increasing a lag behind the real time. So how do we do that? Well, we were able to use our existing infrastructure. So we had this Kubernetes cluster, and one of the sort of great things about Kubernetes, it's very easy, especially we're hosted on these sort of cloud providers, to add new node pools, so new sort of clusters of VMs. So we could very easily add a whole sort of set of these large GPU machines to run all these jobs. Partway through the project, Microsoft actually added the ability to scale node pools down to 0, which was fantastic because we weren't running any of this processing at night because it was too hard. Our sort of algorithms weren't able to detect images reliably. So our node pools could like reliably turn off all the VMs, scale down to 0. But it also meant while we were running jobs in the day, if a job was taking longer than expected, rather than forming a sort of queue behind, we would automatically add new nodes to the cluster, which would sort of step in to meet the demand. So once we've processed all of that, we get stored in our existing database, and we can feed back sort of counts of all the objects, our pedestrians, bikes, vehicles, back to GLA and TfL via our existing REST API. Maybe an interesting insight is the fact that we sort of used Terraform and Helm for this was super useful when we actually started hitting kind of subscription limits on Azure for how many virtual machines we could have span up of various kinds. And we were able to get around this by just spinning up new sort of instances of the entire system in new subscriptions to take over some of the processing work. So once we sort of did this, had our raw count data, we tried to make this information as sort of easily accessible to TfL in particular, who were sort of interested in using this in some of their control, in one of their control rooms. So we developed this dashboard where people could come and sort of click on any of the sort of camera locations and see a nice sort of graph of all the kind of object counts throughout the day. So here at the bottom right of the screen, for example, you can see the number of people like slowly climbing over this date. So once we sort of had this in place, the camera team managed to get their hands on a lot of metadata about the cameras, telling sort of information about the camera orientations. And they then started using some human labeled anchor points on the roads to sort of start doing some camera calibration with these 900 well, actually a subset of these cameras, mostly in central London. And this allows us to map from sort of pixel coordinates to real world coordinates. So we could really start asking questions now about how is pavement space being used by pedestrians? You know, where are people actually walking? And start evaluating policy changes, such as when streets have been extended, are people now using, making use of this space to actually socially distance? So this figure on the left, the top row shows you a sort of heat map of pedestrian activity over a few weeks, and on the bottom shows you the same after these roads have been extended by sort of Transport for London to allow people to socially distance easier in busy areas. Finally, because we have these real world coordinates, we can start mapping these out on satellite images to sort of make it a little bit easier to see these. And finally, and possibly the most interesting use of the system, is we could then start identifying pedestrians and measuring sort of social distancing between people in the scenes from this real world coordinate system. So here we sort of detecting, where are all the people? We detect whether they're in groups. We sort of measure the distance between people in those groups and the different distance between various sort of groups of people in the scene. So in terms of impact, well, as of the start of September, we'd processed about 19 terabytes of footage. We've identified about 24 billion objects in these samples. Transport for London and the Greater London Authority have been using this system to inform policy interventions, such as increasing space for pedestrians on busy footpaths. And the team are currently writing a paper where they're using sort of historical data to evaluate how busyness in different areas and social distancing changed during the sort of start and end of different policy interventions, such as the Ease Out to Help Out scheme, and more micro interventions where road sort of pedestrianized and road areas have been reconfigured. So just to sort of finish, to reflect on how we were able to sort of do this in the time we had. So we were able to go from project, the idea of the project to having data coming back to GLA in a matter of months. Sort of the key factors there, I think, were data readiness. So we because of this this air pollution project, we already had sort of appropriate data for the task. It just happened that we could sort of reuse this to answer these sort of questions. We had a lot of our infrastructure and pipelines in place. Extremely important with the camera data is we already had quite a lot of knowledge and understanding of the sort of legal constraints and privacy considerations around these camera footage. So the TFL is sort of publicly available and low resolution. We did look at using other data sources. So we were in touch with a lot of the boroughs in London who have huge amounts of CCTV, but these are often at much higher resolution. And it took almost the entire length of the project just to sort of understand the kind of ethical concerns around those data sets and how we would actually preserve privacy in those. So they sort of never made it into the project while I was there. The other addition was our sort of existing and scalable infrastructure. So because we were doing this on Azure on the cloud, it was relatively easy to add large amounts of compute. Again, as long as you can sort of finance it. And we were in the very lucky position that Microsoft had sort of donated a large amount of credits to the Turing Institute that we were able to leverage. Our sort of use of Kubernetes made it very easy to sort of scale this and add more infrastructure in a very sort of reliable and quick way. And this really meant that our RSE team could focus on onboarding the sort of researchers and sub-teams, making sure they had the right data access and could provide support rather than having to focus on really building this infrastructure from scratch. And I think with about 30 seconds to go, that is me. Thank you very much.
Fantastic. Thank you, Oscar. Thank you, Oscar. We've got a few questions for you. So, yeah, if anybody wants to upvote any of these questions quickly. First one on the list at the moment is, do you know how many GPUs you used on average and how much did that cost?
Yeah, absolutely. So the it's sort of varied throughout the project for sort of day-to-day running. I think our camera processing came online at about 5 a.m. And finished probably about 8, 9 o'clock in the evening. Kind of varied throughout the year, but I think we were using about 8 NC24 machines on average during the day, which would sort of scale up and down a little bit. We did have periods where we had to sort of back process some missing data, and then we sort of scaled those up pretty considerably. And we also had a few other GPUs that were being used for development. So we'd probably be operating within the sort of 8 to 12 machines during the day on average.
Okay, cool. And is the system still running? And is it something that would be useful post-COVID?
Absolutely. So the system is still running now. There is a hope that I think we're hoping it's like slowly becoming redundant and can be scaled down. It absolutely will be something useful post-COVID. So all the work that we've done here is sort of feeding back into our evolution forecasting project anyway. So we learned a huge amount about how to do this at scale, what the sort of challenges were, and they're all sort of feedback into making our evolution forecasts more sort of accurate.
Okay, excellent. And have TfL got cameras that you could use in the underground for pedestrian stuff, I guess?
Yeah, so we did have a lot of discussions about at the start of the project, we really wanted to expand to lots of different data sources. So we were talking to GLA about getting mobile phone data, tap-ins from on the tube stations and sort of cameras in the underground, which they absolutely do have. But the large problem we sort of faced was really being able to leverage these quickly, which was easy with our other data sources because we'd already sort of solved data sharing agreements, all the rest. Generally with the cameras, it came down to how we deal with the sort of downsampling to preserve privacy, and also how we tap into those systems. So with TfL, it's quite easy to get access to these public cameras. For the Scoot data, we had to go into Transport for London's offices and work with them to actually like tap into the system. And we sort of had all those sort of constraints. So it's really time and privacy constraints that stopped us doing it at that time. But it's absolutely something you could do.
Okay, excellent, thank you. And how many people would be needed to sustain and maintain the system if it went into production post-COVID?
So it's a good question. So the vast majority of the work from the RSE team happened over the sort of summer in 2020, and we scaled down, and it was sort of left with the researchers to maintain it, and an RSE called James Brandreth, who I think's just got a job at UCL. So after a while, sort of James Brandreth and a couple of the researchers who'd become very sort of comfortable with the system were essentially just maintaining the whole thing. So it was able to be maintained by sort of 1 or 2 people really, who were also doing other work on the side as well. It wasn't like a full-time role for them.
Okay, brilliant. Thank you very much. So that's all the questions we have. I'd just like to thank you very much, Oscar, for your talk, and thank you, Luke and Ben, for yours as well. I think everybody was, I was very pleased. I enjoyed them all very much. I guess we'll see everybody again for the next session tomorrow. We're going to have a workshop session tomorrow morning at 10 o'clock. If we don't see each other in the Gathertown venue, where I've still got to find some coins and work out how to decode them. So if anybody's got any clues they can help me with, then I would appreciate that myself. So maybe I'll see you there again. Anyway, thank you everybody, and thank you all for coming along this afternoon. See you and on.